statistical learning, Bayesian learning from high-dimensional data, including preferences and recommendations. He obtained his PhD from Paris-Dakar University, which is also known as Paris 5. Right, Aghiles?
Thank you. So, hi everyone. Thanks for coming. So, today we'll introduce a new model called C2PF, which is a personalized recommendation model. So, it's a Poisson latent factor model of user preference with item context. So, Hady mentioned a lot about different modalities. So, the modalities that we will consider in this work are the user preference and the item context. My planned presentation will be very simple. I will just give a brief overview of personalized recommendation that Hady already introduced very well. And then I will present the C2PF model, give some experimental results, and conclude. So, as mentioned before, the reason why we want to do personalized recommendation is that web application nowadays offers so many options. So, as example, in Amazon, for the word data science, there are over 50,000 possibilities. So, it's not reasonable to go through all these possibilities one by one to make a choice. So what we would like to have is some intelligent system that can capture our preference and reduce the number of possibilities from 50,000 to a reasonable number like 20 or even 50 or something that we can process in a reasonable time. So the key to personalized recommendation is the so-called user preference matrix or user item interactions. So the idea is that given a set of users and given a set of items, we start to record the interaction between those two sets of objects. So for example, it could be that we are interested in recording the ratings that users provide to different items. It could also represent some implicit information like clicks, purchase, etc. So the idea is based on this information or user item interaction is to extract some latent information that could help us characterize the user behavior. So for example, a well-known personalized recommendation in practice is what is called matrix factorization. So it's a kind of a variant of the singular value decomposition, SVD, that Hady introduced before. So the idea is that given our preference matrix, we look or we seek to learn some user factors which are latent and some item factors whose product can reconstruct the original user preference matrix. Now, you can think of the user factors and item factors as embeddings, like just as Maksim introduced embeddings or vector for words, here we will have embeddings or vectors for users and items. Now, the good thing about this approach is that if I have a user vector, an item vector, then their product will give me some score that I can consider as the user preference to that items. It means that when there are unknown ratings in our data, we can predict them by using the product of the user and item factor that we just learned. Now, although successful, this approach has some drawbacks. The first one is that in practice, the user-item interaction will be very sparse, meaning we will be recording only very few user-item interactions. And the problem is that it is very difficult to learn useful information from such past data. In particular, it is also possible that the user-item interaction do not cover all aspects of user behavior. Like it could be that the user is interested in an item because another friend recommended that item, not necessarily because that item fits the preference of that particular user. Another challenge is the difficulty to generalize the preference of a user given very few interactions. So for example here, user 1 provided only one rating. It's very hard to generalize the preference of this user based on only one interaction. So, in order to overcome this issue, researchers started to explore other sources of information. So, in the previous talk, Hady mentioned about social network information. So, this is one of the modalities that the researchers have been exploring a lot to supplement the sparse user-item interactions. Now, other possibilities include item content. It could be, for example, the item description, images, or either the item features. So that constitutes another source of information that could be useful to supplement the lack of user preferences. So in this talk, or in this work, we are interested in integrating item relatedness. Now, the first question is how to capture this item relatedness, or where to find this item relatedness. Because we saw that for features it's easy, we just have to look for the description of the items or to collect the images. For the social network is the same, we just need to collect the user connections, but how can we capture this item relatedness? So this will bring us to the notion of contexts that Maksim introduced in the context of words. So in the case of words, a context is just a sentence, and words co-occur in a sentence. Now the good thing is that we can use the same concept for items. Like if we can view items as words, so then we can start to define somehow a context in which item may co-occur. So as a first example of a context, we can consider a shopping cart. So intuitively, items that occur together in a shopping cart are likely related to one another. So here, for example, we can have a pair of shoes that matches well a shirt and a pair of jeans. Now, another example is a browsing session. So when we shop, for example, for a phone online, we usually try to consult or browse different kind of items before to make a choice. So here is an example of a browsing session on Amazon where we see phones of different types and brands. Now finally, another example of context in which items may occur are song playlists. So here is the same. Intuitively, items that occur or co-occur within the same playlist are likely related to one another. So for example, they may share the same a coherent theme. So to sum up, it seems like this notion of context that could be application specific, even a shopping cart, a browsing session, or a music playlist, encode some useful information about how items are related to one another. So the idea is that we will try to use this notion of context to capture item relatedness and to even incorporate this item relatedness to personalized recommendation. Okay, so before to describe C2PF formally, I would like to give the intuition or the underlying intuition behind C2PF. So based on the examples that we just saw, we suppose that there could be two reasons why a user may prefer an item. So let's take, for example, this particular example where we would like to know why a user may like this shirt. So we posit that the first reason is that the latent preferences of that user matches the item attribute. It corresponds to the preference of the user. This is the classic one and the so-called collaborative filtering. Now, in addition, so this information can be captured using the user item preference matrix. Now, in addition to this information, we posit that this preference could also be explained by the fact that the user preferences matches the attribute of other related items. So as a user, I may like this shirt because I like these pairs of jeans, or because I like the shoes, and because these items work well together, I may consider to prefer this shirt. Now, the idea behind C2PF is to combine these two sources of information to explain user preference in a joint framework. Okay, so here is a representation, or a more formal representation of the matrix factorization that I have introduced before. So here the nodes represent latent variables. So the difference with neural networks is that the nodes here are not deterministic, but they are instead stochastic, meaning that they represent latent variable. In the language of statistics, we call this kind of representation a graphical model. So the idea here is that given some observed data, so X here represent the user item interactions, we represent the dependencies of the different variables. And here theta represent the user factors and beta represent the item factors. So what do we mean by this representation is that the user item interaction are explained by user factors and item factors. So this is basically matrix factorization in a more formal representation. Now, this part alone represent what we call collaborative filtering, meaning that we only make use of user item interactions. Now, C2PF builds on this framework of matrix factorization. Now, in addition to this user item preference matrix, we would like to leverage item relatedness. So we will introduce a new set of latent variable that can capture this notion of item relatedness. So now, this is C2PF. Okay, so we have a couple of new things. The first new thing, is what we call the context factors, right? So for example, following the illustration I gave before, beta or the item factor may represent the shirt. Here, the context factors may represent the factors or the embeddings of the pairs of jeans and the pairs of shoes. Now, in addition to these context factors, we also consider what we call the context effect. So intuitively, this context effect measure or capture the strength of the relationship between two items. It's true that two items that co-occur in the same context are likely related, but we can expect to have different degree or different strength of item relatedness. So then we introduce this new context effect to capture this notion. Finally, we also consider what we call the average context effect. So the idea or the intuition behind this new representation is to capture the fact that For example, some shopping cart may contain many more items than other shopping carts. So we would like to capture this difference in context length. Okay, so far we introduced the dependencies between the different latent variables. So this is C2PF. So now I will just enumerate the different distributional assumptions that we make behind these different nodes or variables. So I mentioned that these nodes, computational nodes, represent actually random variables. So we do put some assumption on the distribution of this random variable. So we suppose that the integer ratings here, x, u, I, come from a Poisson distribution. So a Poisson distribution that depends on our set of latent variables or latent factors or even embeddings if you want. So now we note two important things. The first kind of interaction are user and item interaction. This is basically traditional collaborative filtering. Or this part only takes into account the user item preferences. In addition to this first interaction, we also consider the notion of context. So here the user will also interact with the context or the item that occur in the context of item I. Now the idea here is exactly the intuition I mentioned before, that the user preferences are driven by two main components. The first one is the interaction between the user and the user preference and item factors. The second one is the interaction between the user and other related items to our item of interest, meaning beta I. Okay, so now the first layer of latent variable are all supposed to be gamma distributed. So this is basically a technical choice because the gamma is a conjugate prior to the Poisson. So to make it simple, if we choose a gamma, we will make things more easier later. Finally, the last layer of latent variable, or the average context effect, is the inverse gamma. Similarly, this is a technical choice to make things easier later. Okay, so C2PF is more just than a unique model. Now, starting from C2PF, you can derive other kind of learning algorithm by changing specific components. So, for example, in our case, we study what we call tied C2PF. So basically, the difference with C2PF is that we assume that the context factors and the item factors are the same, whereas in the original formulation, we introduce a different set of parameters. So basically, in tight C2PF, you will have less parameter to deal with. Now, another one that we study is called reduced C2PF, where we simply remove the item part and assume that the user preferences are explained based on the item context alone. So what we're trying to say with this variant is that even if you don't have access to the user-item interaction, you can still perform personalized recommendation by considering the context of a specific items, meaning that even if a user didn't rated items, or he rated only a few items, we can still rely on the context of those items to make recommendations. Okay, now the question that arises is how do we get to perform recommendations or to provide recommendations with C2PF in practice? So all what we need is a quantity or a probability which is called the posterior distribution. So basically we need to compute this quantity, like the probability of the latent variable theta, beta, and so on, given the observation. So here X represents the user preference and C represents the item context information. Unfortunately, this quantity is intractable in practice, meaning that we cannot compute it in a reasonable time because of some integrals in the denominator of this probability. So in order to overcome this difficulty, we rely on approximate methods. In particular, we consider what is called the manifold variational inference. So the idea, this is our intractable posterior. So here the red distribution represents the intractable posterior that I just showed you. The idea is to approximate this intractable posterior with a simple but tractable distribution, which is called the variational distribution. Now, how do we approximate this intractable or red distribution with the blue one? Is by using some distance, which is called the Kullback-Leibler divergence. So basically, we seek the blue distribution that best fits the red intractable distribution. Now, once we have this blue distribution, we can estimate missing ratings. So what we do is basically we take the expectation of the user-item interactions. So the expectation here is over the tractable variational distribution plus another term, an expectation, a second expectation, this time, which represent interactions between a user's factor and context factors. So again, you see that this notion of user preference or user-item interaction and item context are reflected in our prediction formula. Okay, so now I will present some experimental results to see whether this notion of item relatedness is really useful for personalized documentation or not. So we basically use 6 datasets from Amazon, which correspond to different categories, like office, grocery, clothing, etc. So this dataset come up with the user item interaction data, meaning that we have a set of users and the rating they gave to the items. We also have some information about the browsing session represented in the so-called also viewed items. So when you do shopping in Amazon, usually they will display a list of items and they will say that users who viewed this item also viewed the set of other items. So it's basically represent the browsing session. So this is what we consider as our context in our experiments. Okay, we also consider a couple of baselines. I will not go into the details of these baselines, but there are a few things that are useful to mention. So the first one is a method that also considers this notion of item relationships, but it uses different assumptions and it uses a different architecture, which is less specific to the notion of item context as C2PF. We also consider Bayesian Poisson factorization. So Bayesian Poisson factorization is basically the collaborative filtering component of our C2PF. So if you remove the item context from C2PF, you will recover Bayesian Poisson factorization. Now, it is important to compare to this one because we can exactly assess whether item relatedness is useful for personalized documentation or not. And then the other two baselines, collaborative topic Poisson factorization, are basically other architectures that can be considered or other modeling alternative that can be used as a substitute to C2PF to model this notion of item context. I mean, I would just like to mention that they have been designed to represent item content, but they could also be used to represent item context. So here we are interested to see whether our modeling assumptions and architecture is useful. Okay, so here are a few results. So the first important thing to note is that the different algorithms, now except PF, Bayesian Poisson factorization, all the other algorithms make use of the notion of item context. Interestingly, we observe that all those algorithms which make use of the notion of item context within the Poisson family perform better than the original or the basic PF, which provides evidence that indeed the item context underlie some useful information that could explain the choices people make. Now we also know that the different C2PF invariants outperform the other algorithm in almost all cases, which also highlights the importance of our modeling assumption or the importance of the C2PF's architecture. Now, we also conducted another series of experiments to understand or to characterize the circumstances in which C2PF provides the most significant improvements. So here we are interested to compare C2PF, the black bar, to PF, the turquoise bar. So the intuition here is we would like to understand when does the item relatedness helps more in terms of personalized recommendation. So here we consider users with different number of ratings, like users with less than 10 ratings, user with the number of ratings between 10 and 20, and so on. So we consider users with different activity. Now, although the results are quite data dependent, we do observe that it seems like the gap between the black and the turquoise bar are more important on users who provided very few ratings. I mean, it makes sense, because when a user has very few interaction, it's very challenging to generalize his preference based on this very few interaction. Whereas, by taking into account this notion of item context, we can generalize the preference of a user to other items of similar context. So, going back to our example of shared engines, if I do express my preference on a shirt, so C2PF can generalize this preference to other related items, like other pairs of jeans, other pairs of shoes. So the results really highlight the importance of this notion of item relatedness to improve personalized recommendation. Okay, so to conclude, we presented C2PF, which is a personalized recommendation approach that also integrates this notion of item relatedness. So from experiment, it seems like item context underlies various aspects that give the user choices. And we also saw that C2PF outperforms other competing methods, which provides positive supports for the assumption and the architectures of C2PF. Now, if you want to know more about C2PF, then there is a paper by Hady and me entitled A Bayesian Latent Variable Model of User Preference with Item Context, which will appear in the ISHCAI proceeding this year. The source code will be released soon, so if you are interested, please feel free to drop me an email. I will be happy to let you know when the code is released. So this code will be released as a part of a new library that we develop, a recommendation library that we develop within the preferred.ir project. Okay, so thank you for your attention. Questions and suggestions are welcome. Okay, so thank you for this question. So the computational scaling, the computational complexity of C2PF is linear with respect of the number of user-item interactions and the number of item-item interactions, meaning that these information are extremely sparse, and in theory, this is the best computational complexity that we can have in terms of this kind of learning algorithms. Yeah. So this is basically a very scalable approach, and it can also take advantage of some parallel computation. I didn't went into details, but the learning algorithm can be decomposed. The computation can be decomposed across users and cross items. So if you have the capacity to do some parallel computation, you can even scale more. Yeah.
Before we end the day, I would like to announce something. Singapore Data Science Consortium has actually invited Research Centre and Institute of Higher Learning to actually showcase their latest technology in terms of data science. It's actually on the date, which is on the screen, the 21st August, whereby industry and also a lot of researchers will come. So we also hope that we can extend this invite to you all. If anybody want to, interested to know more, you can go to our website. Just Google for SDSC, Singapore Data Science, sdsc.sg. Go to our website and register. Or probably you all can even write to Hui Min over here, the contact, or sdsc@nus.edu.sg. And then pre-registered, then we will open it for you. Yeah. And also, I would like to also extend my appreciation to Prof Tan. Prof Tan Yanli is here today. He is from NUS School of Computing. He is also the head of Singapore Data Science Consortium. Really appreciate because he made everything happen also. Yeah, and also Prof Hady and his team. Thank you for everything on the technical talk. And also especially thanks to Data Science SG, Michael, Ku, Kaixin. Yeah, and also Hui Min, thanks for all the logistics that you have done. It was very tiring. Okay, so hope that you all will bring back something with you all and digest a little bit, and in future more learning will come to you. Okay, thank you.